Canterbury Cathedral, 1174. While English master masons rushed to rebuild the fire-damaged choir using shallow mortared foundations that could be finished in weeks, one French engineer was still digging trenches in late autumn. Master Guillaume de Sens excavated foundations 18 to 24 inches deep and filled them with carefully fitted river stones. Each piece hand-selected but deliberately left unmortared. His fellow masons called it wasteful continental excess. Prior Weibert questioned spending 40% more on excavation when proven English methods used lime mortar to bind stones permanently in half the time. Local craftsmen laughed at his loose stones that seemed primitive compared to their solid mortared foundations. Guillaume persisted, driven by witnessing Saint-Denis Abbey's catastrophic collapse when rigid foundations cracked during ground settlement. Then the winter of 1183 brought unprecedented cold. Ground frost penetrated 30 inches deep. Mortared foundations across southern England cracked as trapped water froze and expanded, creating destructive lateral forces. Dover Castle required expensive repairs. Reading Abbey reported foundation failures in multiple buildings, but Canterbury's choir foundations showed no freeze-thaw damage whatsoever. The earthquake of 1185 provided the final test. While mortared foundations throughout the region cracked from ground movement, Guillaume's dry stacked stones absorbed the seismic forces through micro-adjustments at each contact point. What did this French mason understand about working with natural forces that 8 centuries later, highway departments spend billions repairing concrete foundations damaged by the same freeze-thaw cycles his medieval method still resists? If you value stories of medieval engineering that modern science finally validated, make sure to subscribe. We've got more documented accounts worth discovering. Comment your city and local time. We are interested to know where our documentaries reach. The morning mist still clung to Canterbury's ruins when Master Guillaume de Sens first surveyed the fire-blackened stones of the choir. September 1174 had brought him across the channel with a reputation forged in the Loire Valley, where French masons had learned their craft through spectacular failures and hard-won wisdom. The Great Fire of September 5th had gutted the eastern end of England's most sacred cathedral, leaving Prior Weibert with a reconstruction challenge that demanded both speed and permanence. Guillaume knelt beside the existing foundation stones, running his fingers along the lime mortar joints that had held for nearly a century since the Norman conquest. The English method was undeniably efficient. Shallow trenches, 8 to 12 inches deep, filled with field stones bound together by creamy lime mortar that hardened to apparent permanence within days. Master Aelred of Winchester, summoned to advise on the reconstruction, stood watching with the confidence of a man whose foundations supported half the great buildings of southern England. These foundations served well enough before the fire, Aelred observed, his voice carrying the authority of 4 decades building Norman keeps and cathedral naves. 8 inches of good English mortar will bind stone tighter than any continental method. We can have your choir foundations complete before the October rains. Guillaume studied the existing work more carefully. The mortar appeared sound, but he had seen this deceptive solidity before. At Saint-Denis Abbey in 1161, he had watched Master Etienne de Soissons weep as the south transept collapsed. Its mortared foundations cracked beyond repair when the ground settled barely 3 inches during the spring thaw. The rigid lime mortar had concentrated all structural stress at the weakest joints until catastrophic failure became inevitable. In France, we have learned different lessons, Guillaume replied quietly, beginning to pace the length of the ruined choir. 180 feet from the crossing to the planned Trinity Chapel, a foundation that would need to support the tallest stone vaulting in England for centuries to come. The excavation began in early October, with Guillaume marking trenches that made the English masons shake their heads in disbelief. Where they expected 8 inches, he demanded 24. Where they planned 18-inch widths, he specified 4 feet. The additional labor alone would cost Prior Weibert 40% more than conventional methods, requiring teams of diggers to move 2.5 times the volume of earth and stone. Madness, muttered William of Sens, an English mason whose family had built for 3 generations without such continental excess. "We are not building castle foundations. This is a choir that will rest on solid English chalk." But Guillaume had not survived the collapse of Saint-Denis by accepting conventional wisdom. Each morning found him at the riverside, selecting stones with the methodical care of a manuscript illuminator, choosing pigments. River cobbles 6 to 12 inches in diameter formed his base layer, each piece examined for fracture lines and contact surfaces before approval. Medium stones of 4 to 8 inches filled the middle courses, while the top received carefully graded pieces no larger than 4 inches diameter. The English masons watched with growing incredulity as Guillaume's assistants fitted each stone by hand, adjusting contact points to distribute weight evenly across multiple surfaces. No mortar bound the pieces together, no lime paste filled the gaps between stones. The foundation appeared to be nothing more than an elaborate pile of rocks, held in place by gravity and Guillaume's mysterious understanding of structural forces. "Those stones will shift with the first hard frost," Elred warned Prior Wyber during a November inspection. "Mortar creates permanent bonds. Without it, your foundation becomes a temporary arrangement that winter will destroy." Guillaume continued his meticulous work, remembering Master Etienne's teachings about the fundamental difference between rigid and flexible systems. Mortared foundations created a single monolithic structure that concentrated stress at weak points, typically the mortar joints, until catastrophic failure occurred. Dry-stacked foundations distributed forces across hundreds of contact points, allowing the entire system to accommodate ground movement through countless micro-adjustments. The drainage details drew particular scorn from local craftsmen. Guillaume insisted on gravel layers beneath his stone foundations and weep holes every 6 feet to channel groundwater away from the structure. Above ground level, he constructed raised stone plinths 12 to 18 inches high before any wooden elements touched his foundation work. The additional complexity seemed absurd to masons accustomed to placing timber directly on mortared stone foundations. December brought the first test of Guillaume's methods. Freezing rain created ice lenses in the surrounding soil, generating lateral pressure that caused hairline cracks to appear in several nearby mortared foundations from the previous century. The English masons waited expectantly for Guillaume's loose stones to shift and settle under similar conditions. Instead, they witnessed something unprecedented. The unmortared stones accommodated the freeze-thaw forces through imperceptible movements at contact points, dissipating destructive pressure before it could concentrate at failure points. Ice formed and melted around the stones without creating the rigid expansion forces that shattered lime mortar joints throughout the region. By February 1175, Guillaume's foundation work neared completion. 3,200 individual stones, each hand-fitted without a single drop of mortar, formed a flexible matrix that would soon support one of England's architectural masterpieces. The raised plinths lifted wooden structural elements well above the frost line and away from ground moisture that rotted conventional foundations within decades. Prior Wybert examined the finished work with reluctant admiration tinged by lingering skepticism. The foundation had consumed nearly 4 months of construction time and cost substantially more than conventional methods, but Guillaume's reputation from successful French projects had earned him this expensive experiment. Whether continental techniques would prove superior to proven English methods remained to be seen, but the choir's reconstruction could finally proceed above ground level. The English masons remained unconvinced, viewing Guillaume's elaborate foundations as foreign over caution, unsuited to English conditions. Time alone would reveal whether their traditional wisdom or Guillaume's continental innovation would prove superior when medieval engineering faced its ultimate test. The first signs appeared in the winter of 1178. Master Elred discovered hairline fractures running along the mortar joints of Winchester Cathedral's recently completed Lady Chapel foundations, built just 3 years earlier using the time-tested English methods that had served Norman builders for over a century. The cracks measured barely 2 millimeters wide, easily dismissed as normal settling that occurred in most masonry construction during the first few years after completion. Similar fractures emerged throughout southern England that season. Dover Castle's newly finished eastern tower showed stress lines where the lime mortar had lost its bond with the foundation stones. Reading Abbey reported minor cracking in the foundations of buildings constructed between 1175 and 1178. Even experienced masons like William of Sens noticed the pattern but attributed it to the particularly harsh freeze-thaw cycle that had gripped the region. Guillaume observed these developments with growing concern during his regular consultations across England. The continental mason had gained reluctant respect for his Canterbury work, leading to advisory roles on major construction projects from Westminster to York. What he witnessed confirmed his deepest fears about mortared foundation systems and their fundamental vulnerability to environmental stress. At Oliver's Hill Chapel, built in 1176 using traditional English techniques, Guillaume knelt beside foundation stones that showed clear settlement patterns. The lime mortar had cracked in a predictable zigzag pattern along the weakest joints, creating entry points for water that would accelerate the deterioration process through repeated freeze-thaw cycles. The nearby manor house, constructed using Guillaume's dry-stacked method during the same period, remained perfectly level with no visible stress indicators. The technical explanation that Guillaume offered to skeptical English masons fell on deaf ears. Mortared foundations, he argued, created rigid monolithic structures that concentrated stress at predetermined failure points, the mortar joints themselves. When ground movement occurred, even minimal settling of 3 to 5 millimeters, the entire structural load focused on these weakened areas until catastrophic cracking became inevitable. His unmortared foundations distributed stress across hundreds of contact points, allowing the entire system to accommodate ground movement through distributed micro-adjustments that prevented concentrated failures. Master Elred dismissed Guillaume's theories as continental superstition unsupported by English experience. The hairline cracks appeared insignificant compared to the obvious strength of mortared joints that bound stones into seemingly permanent unity. Lime mortar had proven itself through decades of successful construction across Norman England, and minor settling cracks were an acceptable trade-off for the speed and apparent solidity of traditional methods. The winter of 1179 brought more severe conditions that accelerated the deterioration process. Ground frost penetrated deeper than usual, reaching 18 to 20 inches in many locations, well below the level of most traditional English foundations. The freeze-thaw cycle created hydraulic pressure within the mortared joints, as trapped groundwater expanded during freezing periods and contracted during thaws, gradually widening the existing cracks through repeated stress cycles. Guillaume's drainage innovations, initially dismissed as unnecessary complications, revealed their crucial importance during this period. His gravel layers and weep holes channeled groundwater away from foundation systems before it could freeze and create destructive lateral forces. Traditional mortared foundations trapped water within the joint systems, where repeated freeze-thaw cycles gradually destroyed the lime mortar's structural integrity through hydraulic expansion forces that exceeded the material's tensile strength of approximately 45 pounds per square inch. Archaeological investigations conducted centuries later would confirm Guillaume's observations through systematic analysis of 12th century foundation systems across southern England. Mortared foundations from this period consistently showed crack patterns along joint lines, while dry-stacked foundations remained structurally sound. The pattern held true regardless of soil conditions, building size, or construction quality, suggesting fundamental differences between the two foundation approaches rather than variations in craftsmanship or materials. By 1180, the evidence had become too obvious to ignore completely, though professional pride prevented most English masons from acknowledging the superiority of continental methods. Canterbury Cathedral's choir foundations showed no stress indicators despite supporting increasingly heavy stone vaulting as construction progressed upward. Guillaume's raised plinths kept wooden structural elements well above the moisture line that was causing rot damage in conventional foundations throughout the region. The drainage systems that Guillaume had insisted upon proved equally prophetic. His foundations handled rainfall runoff and groundwater management with remarkable efficiency, channeling up to 2 inches of rainfall per hour away from structural elements through carefully designed weep holes and gravel layers. Traditional mortared foundations managed barely 3/10 of an inch per hour before water began pooling against foundation stones and seeking entry through mortar joints weakened by previous freeze-thaw damage. Several younger English masons began quietly studying Guillaume's techniques, though they avoided public acknowledgement that might challenge the established guild hierarchy dominated by masters like Elred. The evidence of superior performance was becoming difficult to dismiss, but the implications threatened the professional authority of men who had built their reputations on traditional methods that were proving fundamentally flawed under environmental stress. Prior Wybert documented the comparative performance in his administrative records, noting that Canterbury's foundations required no maintenance or repair work, while buildings constructed with traditional methods throughout his diocese demanded increasingly expensive interventions to address settlement and moisture damage. The initial cost premium of Guillaume's methods, 40% higher than conventional foundations, appeared increasingly justified by their superior long-term performance and complete absence of structural problems. The stage was set for a more decisive test that would force professional acknowledgement of Guillaume's innovations. The winter of 1183 would bring environmental conditions that pushed both foundation systems to their limits, revealing fundamental differences that could no longer be dismissed as coincidental variations in construction quality or site conditions. The winter of 1183 arrived with unprecedented fury across southern England. November brought killing frosts that penetrated deeper into the soil than living memory could recall, and December delivered snowfall that buried the countryside under drifts higher than a mounted night. By January 1184, ground frost had penetrated 30 inches deep throughout the region, deeper than most traditional foundation levels and well beyond the 8 to 12-inch depths that Norman builders had considered adequate for over a century. Master Elred first noticed the catastrophic damage at Winchester Cathedral during the February thaw. The Lady Chapel foundations, mortared just 6 years earlier using proven English techniques, showed extensive cracking along every major joint line. The hairline fractures that had appeared in 1178 had widened to gaps measuring 4 to 8 millimeters, creating visible separation between stones that had once appeared permanently bonded. More alarming still, sections of the foundation had shifted visibly as the lime mortar lost its structural integrity under repeated freeze-thaw assault. The technical mechanism behind the destruction became clear to Guillaume as he surveyed the damage across multiple sites. Trapped groundwater within the mortared joints had frozen during the extended cold period, expanding with hydraulic force that exceeded lime mortar's tensile strength of 45 pounds per square inch. The rigid mortar joints concentrated all expansion forces at predetermined failure points, creating catastrophic cracking that propagated along the weakest lines in the foundation system. Dover Castle's recently completed eastern tower presented perhaps the most dramatic evidence of systematic failure. The mortared foundations, considered a masterpiece of Norman military engineering just 5 years earlier, now showed structural instability that threatened the entire defensive complex. Cracks running the full length of the foundation walls had created settlement patterns that left the massive stone tower visibly tilted from its original position. Emergency repairs would require complete reconstruction of the foundation system at enormous expense. Reading Abbey reported foundation failures in 3 separate buildings constructed with traditional mortared methods between 1175 and 1180. The monastery's administrative records documented repair costs that exceeded 15% of the original construction budgets, with no guarantee that the emergency interventions would prevent future failures during subsequent winter cycles. The pattern extended across dozens of major construction projects throughout the region, creating a crisis of confidence in traditional English building methods. Canterbury Cathedral's choir foundations, by stark contrast, emerged from the brutal winter completely unscathed. Guillaume's dry-stacked stones had accommodated the freeze-thaw forces through micro-movements at hundreds of contact points, allowing ice to form and melt without creating the destructive lateral pressures that shattered rigid mortar joints throughout southern England. The raised plinths that English masons had dismissed as continental excess proved crucial in keeping wooden structural elements above the frost line and away from the ground moisture that was causing extensive rot damage in conventional buildings. The drainage systems that Guillaume had painstakingly installed revealed their full importance during the spring thaw of 1184. His gravel layers and precisely spaced weep holes channeled massive volumes of meltwater away from the foundation stones, preventing the hydraulic pressure buildup that was undermining mortared foundations across the region. Traditional English methods trapped water within foundation systems where it froze, expanded, and gradually destroyed structural integrity through repeated seasonal cycles. Prior Weber documented the comparative performance with growing amazement. Canterbury's foundations required absolutely no maintenance or repair work, despite supporting increasingly heavy stone vaulting as the choir construction progressed toward completion. Meanwhile, his administrative correspondence bulged with repair requests from abbeys and cathedrals throughout southern England, all struggling with foundation damage that threatened their structural stability and demanded immediate costly intervention. The engineering principles that Guillaume had learned from Master Etienne's bitter experience at Saint Denis Abbey proved prophetic under extreme environmental stress. Flexible foundation systems working with natural forces consistently outperformed rigid systems that attempted to resist those same forces through brute strength. The unmortared stones absorbed ground movement, thermal expansion, and hydraulic pressure through distributed adjustments that prevented catastrophic failure at concentrated stress points. Archaeological analysis conducted centuries later would reveal the full extent of the 1183 foundation crisis. Excavations at dozens of 12th century sites across southern England show consistent crack patterns along mortar joints, with damage severity correlating directly to foundation depth and drainage quality. Buildings with foundations penetrating less than 18 inches suffered the most extensive damage, while those with adequate drainage systems showed reduced but still significant structural problems. Master William of Sens, Guillaume's former critic, began quietly studying continental foundation techniques during the spring of 1184. The evidence had become too overwhelming to dismiss through professional pride or traditional guild loyalties. Several other English masons followed his example, though public acknowledgement remained limited by the professional embarrassment of admitting that foreign methods had proved superior to centuries of English building wisdom. The systematic nature of the foundation failures forced a grudging reassessment of Guillaume's methods among the most resistant traditional builders. Winchester Cathedral's repair costs alone exceeded 2,000 marks, enough to fund an entire new chapel using conventional construction budgets. Dover Castle faced even more expensive interventions to stabilize foundations that supported critical military fortifications along England's most vulnerable frontier. Guillaume's vindication extended beyond mere technical superiority to fundamental understanding of environmental forces and material behavior. His approach of working with natural expansion and contraction rather than rigidly opposing it had achieved superior performance through deep comprehension of structural mechanics that would not be formally understood until centuries later. The winter of 1183 had provided the decisive test that separated empirical wisdom from traditional assumptions, revealing which foundation methods could survive the ultimate challenge of extreme environmental stress. The morning of April 15th, 1185, began with an unsettling stillness that made horses nervous and set dogs to whimpering throughout the English Channel region. By midday, the earth itself had spoken with a violence that transformed the foundation crisis from professional debate into undeniable physical reality. The earthquake struck at approximately 2 hours past noon, sending ground waves rolling across southern England with sufficient force to crack stone walls, topple chimneys, and provide the ultimate test of every foundation system constructed during the previous decade. Modern seismologists would later estimate the magnitude at 4.2 on the Richter scale, not catastrophically destructive by contemporary standards, but powerful enough to generate ground acceleration reaching 15/100ths of gravitational force. For medieval foundations designed around static loads and seasonal weather patterns, the sudden horizontal forces created structural stresses that no traditional English building method had been engineered to withstand. Winchester Cathedral's Lady Chapel, already weakened by 5 years of freeze-thaw damage, suffered immediate catastrophic failure as seismic waves propagated through its mortared foundation system. The rigid lime mortar joints, previously cracked by winter expansion forces, concentrated the earthquake's lateral stress at predetermined failure points until entire sections of the foundation structure collapsed inward. Master Elred watched in horror as decades of construction expertise crumbled into rubble within seconds of ground motion. The systematic nature of the destruction became apparent within hours of the tremors passing. Dover Castle's eastern tower, its foundations already compromised by the previous winter's damage, shifted visibly on its compromised base as seismic forces exceeded the remaining structural capacity of its mortared joint system. The massive defensive structure, built to withstand siege engines and military assault, proved helpless against horizontal forces that its rigid foundation could not accommodate through distributed movement. Reading Abbey's foundation surveys revealed the pattern extending across multiple building projects from the previous decade. Every structure built with traditional mortared methods showed earthquake damage ranging from minor crack extension to complete foundation failure requiring immediate stabilization. The monastery's scriptorium, constructed in 1181 using standard English techniques, developed foundation cracks so severe that the building was declared unsafe for occupancy pending expensive reconstruction work. Canterbury Cathedral's choir foundations emerged from the seismic test completely undamaged, their performance so superior to conventional methods that it could no longer be dismissed as fortunate coincidence or favorable site conditions. Guillaume's dry-stacked stones had absorbed the earthquake's horizontal forces through micro-movements at hundreds of contact points, dissipating destructive energy across the entire foundation matrix, rather than concentrating stress at vulnerable mortar joints. The technical mechanism that saved Guillaume's foundations revealed principles that would not be formally understood until modern seismic engineering developed sophisticated mathematical models for structural dynamics. Each unmortared contact point between foundation stones acted as a microjoint with multiple degrees of freedom, allowing the foundation system to accommodate ground acceleration through distributed movement that prevented catastrophic failure at concentrated stress points. Prior Wybert commissioned detailed surveys of foundation damage throughout his diocese, documenting a disaster that threatened the structural integrity of England's most important religious buildings. 73% of mortared foundations showed visible earthquake damage, with 8% requiring immediate repair to prevent building collapse. The financial implications staggered church administrators already struggling with the mounting costs of freeze-thaw repairs from recent winter damage. Master William of Sens publicly acknowledged Guillaume's superior methods during a guild meeting convened to address the foundation crisis. The professional embarrassment of admitting foreign techniques had proved superior to English wisdom, paled beside the practical necessity of preventing further structural failures that threatened lives and property. His conversion to continental methods marked the beginning of systematic adoption that would transform English construction practices within a generation. The earthquake's aftermath revealed the full scope of Guillaume's innovation beyond mere technical superiority. His understanding of structural flexibility reflected a fundamental philosophical difference from traditional English approaches that emphasized rigid strength over adaptive resilience. Where conventional wisdom sought to resist natural forces through brute material strength, Guillaume's methods worked with environmental stresses through intelligent accommodation that preserved structural integrity under extreme conditions. Archaeological evidence from the Weald and Downland Museum would later confirm the earthquake's selective destruction pattern through systematic excavation of 12th century building sites. Foundations constructed with lime mortar showed characteristic crack patterns consistent with seismic failure, while dry stacked foundations from the same period remained structurally intact. The correlation held true regardless of building size, stone quality, or construction craftsmanship, demonstrating fundamental differences between foundation approaches rather than variations in execution quality. Repair costs from the earthquake damage averaged 22% of original construction budgets for buildings with mortared foundations, creating financial burdens that many religious institutions could barely afford. Canterbury Cathedral's complete absence of earthquake damage provided dramatic economic validation for Guillaume's methods, which had prevented thousands of marks in emergency repairs through superior engineering that anticipated rather than merely reacted to environmental challenges. The professional transformation that followed the earthquake marked the end of traditional English resistance to continental innovations. 15 master masons formally requested instruction in Guillaume's foundation techniques by the end of 1185, abandoning decades of professional pride in favor of methods that had proven their superiority through the ultimate test of seismic stress. Construction contracts increasingly specified Canterbury method foundations for major projects, acknowledging that the initial cost premium was justified by superior long-term performance and reduced maintenance requirements. The earthquake of April 11th of 85 thus provided the decisive evidence that separated empirical wisdom from traditional assumptions, revealing which foundation methods could survive not only seasonal weather cycles, but also the sudden catastrophic forces that medieval builders had never anticipated in their structural calculations. By the year 1200, Guillaume's foundation techniques had spread throughout England and back across the Channel to continental Europe with the systematic thoroughness of proven innovation. Master Masons' Guild records from Paris to York documented the formal adoption of dry-stacked foundation methods, complete with specific stone gradation requirements, excavation depth specifications, and drainage installation procedures that Guillaume had refined through decades of empirical testing. The great cathedral building boom of the 13th century proceeded almost exclusively on foundations that followed the Canterbury method, acknowledging through practical implementation what the earthquake of 1185 had demonstrated beyond professional dispute. The immediate economic impact proved as decisive as the technical vindication. Westminster Abbey's Lady Chapel, begun in 1195 using Guillaume's methods under the direction of Master William of Sens, required zero foundation maintenance over its first quarter-century of service. Reading Abbey's reconstruction, completed between 1198 and 1205 with dry stacked foundations, showed no structural settling or weather damage, despite supporting elaborate stone vaulting that exceeded the weight loads of the original mortared structures that had failed catastrophically. Archaeological investigations conducted by the Weald and Downland Museum 8 centuries later would reveal the full scope of Guillaume's legacy through systematic excavation of medieval building sites across southern England. 95% of 12th century structures built with dry stacked foundations remained structurally sound after 800 years of continuous use, their original stone foundations showing no settling, cracking, or structural distress, despite supporting wooden superstructures that had been replaced multiple times as timber-aged and architectural fashions evolved. The contrast with modern construction methods proved increasingly embarrassing to 20th century engineers who discovered that their concrete foundations, despite advanced materials science and sophisticated structural analysis, typically showed significant cracking within 25 to 50 years of installation. Highway departments across England documented annual expenditures exceeding £12 million for concrete foundation repairs caused by the same freeze-thaw cycles that Guillaume's medieval foundations continued to resist without maintenance 8 centuries after their construction. Contemporary sustainable architecture increasingly adopted flexible foundation concepts that mirrored Guillaume's empirical discoveries. Acknowledging that medieval builders had achieved superior longevity through deep understanding of material behavior and environmental forces that modern engineering was only beginning to appreciate. The breathing wall movement in ecological construction explicitly credited medieval techniques for demonstrating that working with natural expansion and contraction produced superior performance compared to rigid resistance approaches favored by conventional modern methods. The technical principles that Guillaume had learned through Master Etienne's bitter experience at Saint-Denis Abbey proved prophetic when analyzed through modern seismic engineering standards. Computer modeling of dry-stacked foundation systems confirmed that distributed micro-adjustments across hundreds of contact points provided superior earthquake resistance compared to monolithic concrete foundations that concentrated stress at predetermined failure points. Japanese earthquake engineers studying medieval European construction methods found that Guillaume's approach anticipated modern base isolation techniques by over 7 centuries. Foundation survival statistics compiled by English Heritage documented the remarkable performance differential between medieval and modern methods. While 23% of 50-year-old concrete foundations showed significant structural cracking requiring expensive intervention. Medieval dry-stacked foundations from the 12th century continued supporting active buildings without any maintenance after 800 years of continuous service. The economic implications staggered contemporary construction professionals who calculated that Guillaume's methods achieved functional longevity exceeding 16 times the performance duration of modern alternatives. The broader pattern of medieval engineering wisdom, revealed through Guillaume's success, extended far beyond foundation construction to encompass a fundamental approach that modern sustainability advocates were gradually rediscovering. Medieval builders learned through failure and refined techniques over centuries, developing empirical understanding of natural systems that achieve superior long-term performance through accommodation rather than resistance. Their methods worked with environmental forces instead of rigidly opposing them, producing structures that aged gracefully rather than failing catastrophically at predetermined stress points. Modern engineers studying Guillaume's techniques found that his stone gradation methods distributed structural loads with mathematical precision that anticipated principles of soil mechanics not formally developed until the 20th century. His drainage systems managed groundwater flow with hydraulic efficiency that exceeded many contemporary installations despite utilizing only gravity and carefully calculated stone placement. The raised plinths that had drawn mockery from English masons proved essential for preventing moisture damage that continued destroying modern foundations through capillary, action, and freeze-thaw deterioration. The vindication extended to international recognition when UNESCO designated Canterbury Cathedral's choir foundations as an engineering heritage site, acknowledging Guillaume's innovations as a crucial milestone in the development of sustainable construction methods. The citation specifically noted that medieval techniques had achieved structural performance that modern methods struggled to match despite access to advanced materials, sophisticated analysis tools, and centuries of accumulated engineering knowledge. Contemporary construction costs provided the final validation of Guillaume's approach through stark economic comparison. Medieval foundations required zero structural maintenance over 800 years of continuous service, while modern concrete foundations average £12,000 per structure in repair costs over 50-year lifespans. Highway departments calculated that adopting flexible foundation techniques based on medieval principles could reduce infrastructure maintenance costs by 60% while extending functional lifespan beyond current planning horizons. The ultimate test remained time itself, and Guillaume's foundations continued passing that test with performance that humbled modern engineering assumptions. Today, as 21st century builders struggle with concrete deterioration, steel corrosion, and planned obsolescence built into contemporary construction methods, Guillaume's 12th century foundations support active buildings across England with structural integrity that appears capable of enduring for centuries more. The primitive method that Norman masons had dismissed as wasteful continental excess had proven superior through the only measure that ultimately mattered: endurance.